Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to start the fourth unit, analysis of linear systems. Analysis of a linear system. We already know that what is a signal and what is a system. And what is a linear system and what is analysis. So you can analyze the linear system. So before going to the discussion starts with the analysis of the linear system, first of all, you can know what is a signal. Once again, you can recall what is a signal and what are the different types of the signals. So system is a set of elements or functional blocks that are connected together and produce an output in response to an input signal. So what is a system means? A system is a set of elements or functional blocks that are connected together and produce an output in response to an input signal. Means the system is internally there is a functional blocks that are interconnected the components. The functional blocks that are connected together and produce an output in response to the input signal. So what are the signal? There are two types of the systems, continuous time and the discrete time. Continuous time system handles the continuous time signals as an input. Analog filters, amplifiers, attenuators, analog transmitters, and receivers are the examples of continuous time systems. Okay, continuous time system handling the continuous time signals that are analog filters, amplifiers, attenuators, analog transmitters, and the receivers, etc. are the examples of continuous time system. Okay. The output is also the signal, input is also the signal, but it handles the continuous time signals. So we can call it as a continuous time systems. Discrete time system handle the discrete time signals as shown in the figure B here. So the input is a discrete time signal, output is also the discrete time signal, which is analyzed by using the discrete time systems. Okay, what are the types of discrete time systems? Computers, printers, microprocessors, memories, shift registers, etc. are the examples of discrete time systems. Computers, printers, microprocessors, memories, shift registers, etc. are the examples of discrete time systems. They operate only on a discrete time signals. They operate only on a discrete time signals. Okay. A system is a set of elements or the functional blocks that are connected together and produce an output in response to the input signal. There is two types of the systems. One is continuous time system, which handles the continuous time signals, and discrete time system, which handles the discrete time signals. Continuous time systems are analog filters, amplifiers, attenuators, analog transmitters, and the receivers are the examples of the continuous. And computers, printers, microprocessors, memories, shift registers, etc. are the examples of the discrete time systems. So continuous as well as the discrete time system are further classified on the based on their properties. These properties are as follows: the static and the dynamic systems. The property is a dynamicity property, and second one is a time invariant and time variant systems is a shift invariance property. Linear and non-linear system is a linearity property. Causal and non-causal is a causality property. Stable and unstable systems, stability property. Inversible and non-inversible system is an invertibility system. Okay. So first of all, you can take the first one is dynamicity property, that is a static and dynamic systems. Static and dynamic systems. system with memory or without memory. Definition is, the continuous time system is said to be static or memoryless, or memoryless, the instantaneous, if its output depends upon the present input only. Static means the output depends upon the present inputs only, and is said to be a static. The continuous time system is said to be a static or a memoryless, the instantaneous, if its output depends upon the present input only. So it means the y of n is equal to 10 into x of n. Y of n is equal to 15 into x square of n plus 10 into x of n. Means the combination of the input functions. The discrete time system can also be a static or dynamic if the output of the discrete time system depends upon the present input sample only. Then it is called static or memoryless or the instantaneous system. Or here the y of n depends upon only the nth input sample, hence such systems do not need the memory for its operation. When it needs the operation means if it is depends upon the past input also. If it is depends upon the past values, it needs a memory. Because it depends upon the present inputs only, there is no need of the memory. So such type of systems we can call it as a static systems. And what is a dynamic system is? A system is said to be dynamic. A system is said to be dynamic if the output depends upon the past values of the input also. Past value of input means definitely it needs the memory to store the past input. Okay, such type of systems we can call it as a dynamic systems. The output depends upon the present and the past values also. X of n is a present, x of n minus 1. So statics is a continuous time system. Statics as a system means it is a memoryless, no need to store the data because it is depends upon the present input only, or input sample only. Need not any memory for its operation, but dynamic system, it depends upon the output depends upon the past values of the input also. The y of n is equal to x of n plus x of n minus 1. It needs a memory. Okay, dynamic system is. And second one, time invariant and time variant. So what is the definition here? A continuous time system is time invariant if the time shift in the input signal results in the corresponding time shift in the output also. Time invariant means if there is a delay in the input, the output is also delayed. Suppose if I take x of t, the continuous means x of t is the input signal. It passes through the signal system, gets the response is y of t. If the input is delayed with the samples of t naught, which is passes through the system to get the response y of t as y of t minus t naught. If the input is delayed, the output is also delayed, then that system is time invariant system. Time invariant system. Okay. The output is delayed if the input is also delayed. Let y of t is equal to the function of x of t. So when it is passes through the system means y of t, mathematically we can represent y of t is equal to the f of x of t, whichever it is passes through the system. Y of t is a response of x of t if x of t is delayed by the t1 samples. If x of t is delayed by the t1 samples, then the output y of t will also be delayed by the same time. That is, the f of x of t minus t1 is equal to y of t minus t1. The time invariant system do not satisfy the above relation. The time invariant system are also called as the fixed system. If the input is delayed with the t0 samples, but output is not delayed with the t0 samples, means that system we can call it as a time variant system. The time variant system do not satisfy the above relation. Okay, do not satisfy the above relation. If it is satisfy the time invariant system, a continuous time system is a time invariant if the time shift in the input signal results the corresponding time shift in the output. That we can call it as a time invariant, which is not satisfy that condition. We can call it as a time variant system. The time variant system does not satisfy the above relation. Okay. Similarly, the input and output characteristics of the discrete time system do not change with the shift of the time origin. Such systems are called shift invariant or time invariant. In terms of the discrete, it can be represented as x of n. The output y of n. It passes through the function x of n. If n minus n naught is equal to the function of x of n minus n naught. If the input is delayed, the output is also delayed, then we can call it as a time invariant system, which is not satisfy this condition, call it as a time variant system. Got it, my students? Then the linear and non-linear system. Third one, linear and non-linear system. A system is said to be linear if it satisfies the superposition principle. If it satisfies the superposition principle. We know, we've seen the properties in the Fourier series and the properties in the Fourier transformation. A into x of x1 of t plus b into a2 into x2 of t. In the Fourier transformation, we can write as a1 x1 of omega, a2 x2 of omega. So both the functions, the input is the same. Either it is a Fourier series and the Fourier transformation. The input is two functions. If it is a Fourier series, the linearity property. So linearity property. Linear system is related to the linearity property. So a1 into x1 of k plus a2 into x2 of k. And with the same input, a1 x1 of t and a2 x2 of t, apply the Fourier transformation, it becomes of a1 x1 of omega plus a2 x2 of omega. Okay. Now consider the two systems defined as follows. y1 of t is equal to the function of x1 of t, and that is x1 of t is the input and y1 of t is the output. And y2 of t is equal to the function of x2 of t. x2 of t is the input and y2 of the output. Then the continuous time system is linear if the function is the combination a1 x1 of t and a2 x2 of t. The output is a1 y1 of t plus a2 y2 of t. What is that y1 of t? If it is apply the Fourier transformation here, the x1 of k. Like that, the y1 of t is the function of x1 of t. You see here, y1 of t is a function of x1 of t. What is the y2 of t? Function of x2 of t. Got it? Then the system is a linear system. Hence, the block diagram saying that a1 x1 of t this passes through the system, you'll get the y1 of t. Okay, y1 of t is a function of a1 into x1 of t. Similarly, the a2 is multiplied with the x x2 of t, which is passes through the system. Get the output is y2 of t, and adding of the two functions, you'll get the y of t as a1 y1 of t and a2 y2 of t. Okay. Here the a1 and a2 are the arbitrary constants. So this condition states that the combined response due to x1, x2 together is same as the sum of individual responses for the linear system. And similarly, the discrete time system is said to be linear if it satisfies the superposition principle. Y1 of n is equal to the function of x1 of n, and y2 of n is equal to the function of x2 of n. And combining then the discrete time system is linear if the function of a1 x1 of n plus a2 x2 of n is equal to a1 y1 of t plus a2 y2 of t, nothing but y of n is a function of x of n. What is the x of n? The combination of the two functions, a1 x1 plus a2 x2. What is a y1? Is a combination of the two output responses, a1 y1 of 1 plus a2 y2 of n. Okay, my dear students. Next, causal and non-causal system. Fourth one. The definition of the causal and non-causal system is the system is said to be causal if its output at any time depends upon present and the past inputs only. Present and the past inputs only. The causal means it depends upon the present, means x of n. Past inputs means x of n minus 1 or x of n minus 2 and so on. That is, y of t naught is equal to the function of x of t if the t is less than or equal to t naught. Means the t naught is a present, less than or equal to means t naught minus 1, t naught minus 2, t naught minus 3 and so on, because the previous values. Thus, the output at the time t naught depends upon the inputs before the t naught. The causal system is not anticipatory. Similarly, a discrete time system is said to be causal if its output at any instant depends upon the present and the past input samples only. It is y of n is equal to the function of x of k, where k is less than or equal to n. Thus, the output of the function is x of n, x of n minus 1, n minus 2, n minus 3, and so on. For causal system, the system is non-causal if its output depends upon the feature inputs also. Means x of n plus 1, n plus 2, n plus 3, etc. Okay. Causal means the system is said to be causal if its output at any time depends upon the present and the past inputs. That is, a t is less than or equal to t naught, or k is less than or equal to en. Okay. So normally all the causal systems are physically realizable. There is no system which can generate the output for inputs which will be available in the future. Means it is a non-causal or not realizable. Such systems are non-causal and they are not physically realizable. Causal systems are physically realizable and non-causal systems are not physically realizable. Okay, my dear students. Then the fifth one, stability property, stable and unstable system. When every bounded input produces a bounded output, then the system is called bounded input and the bounded output stable, BI and the BO. So what is this criteria here? And the input is bounded. Let us take this mx, the output x of t. The output is also bounded, hence my. Then the system is a stable system. This criteria is applicable for both continuous and the time systems. The input is said to be bounded if there exists some finite number mx. It's a finite number. It is in between of boundary condition less than the infinite always. In the continuous time system, x of t is less than the infinite. In the discrete time system, m of x is less than the infinite. This is a finite value. Less than the infinite is always all the values of the finite only. Similarly, the output is said to be bounded if there exists some finite number my. The y of t is my is less than the infinite in the continuous, and my is less than infinite when the discrete time system y of n. If the system produces unbounded output for bounded input, the system is unstable system. If the system produces unbounded output for bounded input, for every bounded input there is a bounded output, then you can call it as a stable system. If the system produces unbounded output for bounded inputs, then that system is an unstable system. Okay, my dear students. And the last one is invertibility and inverse system. Okay, the definition is a system is said to be invertible if there is a unique output for every unique input. Okay, what is that invertibility? Means the first of all, if you give any input signal x of t to the system, to get the response is y of t. Again, the inverse system, final output is there. So whatever the input is there, the output is also the same. We can call it as a invertibility or the inverse system. A system is said to be invertible if there is unique output for every unique input. If a system is invertible, there exists an inverse system. If these two systems are cascaded as shown in the figure, the final output is same as the input. This is very important. The final output is same as the input. If the system is denoted by the H, then it's the inverse system is denoted by H inverse. Then cascading of the two systems gives H into H inverse is equal to 1. Okay, so finally, this function is 1 only. The 1 into x of t is x of t. Got it, my dear students? So these are the 6 properties we have, or the continuous and the discrete time systems are further classified as 6 types. One is a static and dynamic system, which is memoryless and the memory. Static is a memoryless and the dynamic is a memory. Okay, a continuous time system is said to be static if its output depends upon the present inputs only. If it depends upon the past inputs, then we can call it as a dynamic system, and it needs a memory. Time invariant and time variant means if the input is delayed, the output is also delayed, then that system is time invariant. Otherwise, it is a time variant system. Linear and non-linear system. It satisfies the superposition principle. A1 x1 of t plus A2 x2 of t is equal to is a function of A1 y1 of t plus A2 y2 of t. If it does not satisfy, that system is non-linear system. Causal and non-causal system. A system is said to be causal if its output at any time depends upon the present and the past inputs. Okay, that system is non-causal system. If it depends upon the feature input also, x of n plus 1 n plus 2, then the system is non-causal system. Next, fifth one, stable and unstable system. For every bounded input, there is a bounded output. Then the system is called bounded input and bounded output stable system. Means input is bounded, mx is less than the infinite. The output is also bounded, my is less than input. If the system is unbounded for the bounded input, means that system is unstable system. Next, the last one is the invertibility and the inverse system. A system is said to be invertible if there is a unique output for every unique input. If the system is invertible, there exists an inverse system. If these two systems are cascaded as shown in the figure, the final output is same as the input. The final output is same as the input is nothing but inverse system on the invertibility. Got it, my dear students? Now we discussed the two types of the systems: continuous time system, discrete time system. What is a system and what are the different types of systems? And that two different types of systems are further classified as a 6 types of the systems. Okay, my dear students. Now we go for the frequency response of linear time invariant systems. LTI means linear time invariant system. The linear time invariant system from an important class in the communication, the amplitude and the phase response, reliability, bandwidth, the distortion during transmission of a signal are all very important concepts related to the design and implementation of the systems. Okay, in the linear time invariant system, the amplitude, phase response, reliability, bandwidth, the distortion during the transmission of signal are all very important concepts related to the design and the implementation of the system. So now you can see the frequency response. The frequency response of the system gives the variation of magnitude and the phase of the system output with respect to the frequency on application of the input. You know that the output y of t of the system is given as, the convolution relation. When the x of t, internally there is a linear time invariant system, a linear time invariant system as h of t with input x of t as a continuous. To get the response of y of t, what is a y of t here? The convolution between input and the h of t. We use this formula in the two properties, convolution time of Fourier series, convolution time in the Fourier transformation also, my students. Minus infinite to infinite, the x of t is x of tau, and h of t minus tau d tau. T minus tau d tau. Okay, see here the same thing. Y of t is equal to integral minus infinite to infinite x of tau h of t minus tau d tau. This equation gives time response of the linear time invariant system. Now apply the Fourier transformation on both sides. F of or the Fourier transformation of y of t is equal to the Fourier transformation of the convolution of the two functions, the x of t with the convolution of h of t. See, we know the property, the convolution time combined for the Fourier transformation or the Fourier series. Convolution time is product in the frequency. What is that product? X of f and h is there here, h of f. These are two frequencies. See, the same thing I apply the Fourier transformation for the y of t in the left hand side and the Fourier transformation of the total function. We know that the convolution of two functions is transformed into multiplication of their Fourier transformation. Okay, the convolution of two functions is transformed into multiplication, h of f and the x of f. By applying this, the above function is y of t is equal to k into x of t minus t naught, where k is a constant represents the change in amplitude and t naught is the time delayed in the transmission of the signal through a system. So in the left hand side, the Fourier transformation of y of t is the y of f. So the Fourier transformation is k into x of t minus t naught. K is the constant represents in the amplitude and x is the delayed version with the t naught samples, my students. Okay. From the time shift property of the Fourier transformation, the y of f is equal to k into x of f e power minus j 2 pi f into t naught. So according to the x of t minus t naught, the Fourier transformation, the time shift Fourier transformation is e power minus j omega into T naught x of omega. That's the Fourier transformation in the normal frequency e power minus j 2 pi f into T naught. The shortcut notation is in terms of x of f. So x of f e power minus j 2 pi f into T naught. Got it? And y of f by the x of f means output by the input is transfer function h of f. So h of f is equal to k into e power minus j 2 pi f into T naught. Okay. I take the y of t as with the amplitude k for the constant represents change in amplitude, and the time delay in the transmission of a signal through a system is a time invariant system, my dear students. So its frequency response h of f is equal to k into e power minus j 2 pi f into T naught. This equation gives the transfer function of a distortionless system. It is clear that from the above equation, the magnitude of the transfer function of is k, which is independent of the frequency. That is, the transfer function has a constant amplitude at all the frequencies. Is okay. The phase shift of the above equation is 2 pi f into T naught. 2 pi f into the T naught. The phase shift of the above equation has 2 pi f into T naught. The e power minus is there, so theta f is equal to minus 2 pi f into T naught. That is, the phase shift is linearly proportional to the frequency. If the phase shift is linear at all the frequencies, this can be expressed with the example of x of t is equal to cos 2 pi f into t. Okay. Now let the output signal be the amplitude of by the shifting in time by t naught seconds. Y of t is equal to cos 2 pi f into t minus t naught. Y of t is equal to cos 2 pi f t minus 2 pi f into t naught. So you can compare this equation with the cos 2 pi f t minus pi of f. What is a pi of f? 2 pi f into t naught. That is a minus theta of f, or the pi of f is equal to minus 2 pi f into t naught. So which is proportional to the frequency, the Fourier transformation of a convolution equation x of f and the h of f, where h of f is called the transfer function of the system, y of f is equal to h of f into x of f. Thus, for a linear time invariant system, Fourier transformation output signal is equal to the product of transfer function of the system and the Fourier transformation of the input. The above equation gives the frequency response of the system. Y of f is equal to h of f into the x of f. Got it, my students? For the distortionless transmission through the system, we need a distortionless transmission through the system. A distortionless transmission means the output of the system is an exact replica of the input signal. There is no any distortion, there is no any change in the amplitude, or there is no any change in the phase. That signal is transmitted and received at the receiver. That is nothing but a distortionless transmission, means the output of the system is exact replica of the input signal. The difference between the input and output of such system is that the amplitude of the output signal may increase or decrease by some factor with respect to the input signal. The output signal may be delayed in the time with respect to the input signal because of the system delayed. Therefore, the output signal y of t can be written in terms of the x of t as you see here, the y of t is equal to k into x of t minus t naught. These are response, my students. Okay, that is a distortionless transmission through the system. Okay, my dear students. So frequency response. The distortionless transmission to the system is distortionless transmission means the output of the system is an exactly replica of the input signal. The difference between the input and output of such system is that amplitude of the output signal may increase or decrease by some factor with respect to the input. Either is increasing or decreasing. So I wrote that it is the K, and the output of signal may be delayed in the time with respect to the input signal because of the system is delayed. Therefore, the output of y of t can be written in terms of the input as y of t is equal to k into x of t minus t naught, where k is a constant of represent change in amplitude and t naught is a time delayed version. Okay, apply the Fourier transformation on both sides by using the time shift property here. The x of f is multiplied the negative exponential function, and the ratio between of output by input is nothing but the system function. This equation h of f is equal to k into the exponential function. This gives the transfer function of the distortionless system. It is clear from the above equation that the magnitude of the transfer function is k, which is independent of the frequency. That is, the transfer function has a constant amplitude at all the frequencies. The phase shift of the above equation is what is the phase shift? Theta f is equal to minus 2 pi f into t naught. That is, the phase shift is a linear proportional to the frequency. Here the phase shift is linear to all the frequencies. This can be expressed in another way. Let be the signal in the time domain x of t is a cos 2 pi f into t naught, and the output is relayed the cos 2 pi f t minus t naught. The output y of t is cos 2 pi f into t minus 2 pi f into t naught. And the second term in the cos function considered as a pi of f or the theta of f. Thus the phase shift y of t, the theta f is equal to minus 2 pi f into t naught, which is proportional to the frequency f. Okay, my dear students.